Let's talk moment of inertia. Moment of inertia is an object's resistance to change angular motion. Now we know what inertia is. Inertia we dealt with in linear kinetics, and that's quantified by mass, and that represents an object's resistance to change motion. In this case, moment of inertia is resistance to change angular motion. In fact, almost any time in this class, in physics, when you see the word moment, you actually want to think rotation. So moment of inertia is different than inertia by itself. All right, the equation, and we'll go through this, the equation for moment of inertia is I, is the symbol for it, equals sum of mr squared. In words, all that equation means is we need to know how the mass is distributed about the axis of rotation, and then we can understand moment of inertia. The units come right from the equation. Units of mass are kilograms, and units of r, which will be a distance measure, are units of meters. So that would be squared. So we have kilogram meter squared for units for moment of inertia. And as I mentioned, just to clarify, inertia by itself is an object's resistance to change motion. We quantify that by measuring the object's mass, and the unit for mass are kilograms. Different concept, same concept, just a different world. Inertia we talk about as the general term, mostly applied towards linear kinetics. Moment of inertia is specific to talking about angular kinetics. All right, let's look at the equation a little bit more so we have a good understanding of that. So here's the equation. Right now, you should have also watched the video of the hammer that I talked about for giving an example of moment of inertia. I'm going to draw that hammer right here, and I'm going to rotate that hammer around this axis in this direction. So rotate the hammer like such, okay? And I'm going to concern myself, just for the sake of explaining this, with the hammer being two masses. The end of the hammer, okay, this part right here, and then the handle, which I'm just going to represent as a single mass point, just to get the concept of moment of inertia and how we use the equation over. So this handle has some mass, and the head of the hammer has some mass as well. And right now I'm going to be rotating about this axis of the hammer. To figure out moment of inertia mathematically, I would measure the distance to each mass. It's easier to think where, the distance to the second mass, because that's out at the end. This is a single mass, if you will. We can represent this whole mass with a single point, but in reality, we'd actually have to measure where all these point masses are that make up the entire handle. That's a different thing. We would get into the details of moment of inertia down the road. There's some other ways to get to moment of inertia other than just using this straight up calculation. So if I have this mass here at the end of the object, I would measure this distance, how far it is from the axis of rotation, and I would do the same thing for this point mass, just pretending the handle is a single point, and then measuring where that is relative to the axis of rotation. We get our equation that's going to look like this. I equals sum of mr squared, I equals m1, because we're only going to deal with 2 point masses, times how far that mass is squared, plus m2, how far that mass is squared. So this R2 is squared, and this R1 is squared as well. And we add up the products of mass and the distance squared. So if you look at this equation, this bigger mass being far from the axis of rotation, that's going to make moment of inertia go up. If I do it the other way, which I showed in the video, if I put my axis of rotation here, well, now let's look at that, and let's look at moment of inertia. Okay, a different picture. Okay, and right here, I'm putting the axis of rotation at this point. So now we're going to rotate here. So now we're rotating the object in this plane here. Now I've got this mass here, this mass here. right? And this is the axis of rotation, all right, like that. So I have the axis of rotation, I have the mass, I have the handle mass out in this point here. I figure out that distance for R1, I figure out the distance of R2, which if I'm rotating right at that mass, the R2 is really going to be 0 at that point. So I've got 2 point masses. I use the same equation. Sum of m r squared, m1 times r1 squared, plus m2 times r2 squared. In this case, r2 is really small, maybe even 0. That means this component of that equation gets left out, or it's very small. And the only part that's going to contribute to moment of inertia will be the m1. What that equation tells us is if the mass is closer to the axis of rotation, moment of inertia goes down. The resistance to change angular motion goes down as the mass gets closer to the axis of rotation. The mass is farther from the axis of rotation, it's going to have a bigger impact on moment of inertia. Now, if we rotate the object this way, as I did in that video, and we start looking at how the mass is distributed about that axis of rotation, you can only see a little bit of the hammer. That mass is really close to the axis of rotation. Okay, that we're going to rotate like this. That means those r squareds are going to be really small. And so now the moment of inertia is going to be really low. It's going to be really easy to change the rotational motion of a hammer rotated about this long axis compared to this axis here, or even this axis here. Okay? So moment of inertia is a function of how the mass is distributed about the axis of rotation. The first question we have to ask when we're trying to determine moment of inertia is, where's the axis of rotation? Is it going to be here? Is it going to be here? Is it going to be here? 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 Wherever it is, we then need to calculate how the mass is distributed about the axis of rotation using this equation. Something like this is sort of simple, but in reality we do some other techniques to quantify moment of inertia, but this is the math behind determining moment of inertia. Okay, thanks everybody.